Okay, so let's look at 15.41b from chapter 15 and more spectroscopy. So again, we have the chemical formula C10H14. In the IR, the peak of interest would be at 820 inverse centimeters. We'll talk about the usefulness of that shortly. At 7 parts per million, we have a 4 hydrogen, another broad singlet. At 2.85 parts per million, we have a 1 hydrogen septet. At 2.28 parts per million, we have a 3 hydrogen singlet. And at 1.20 parts per million, we have a 6 hydrogen doublet. All right. So again, let's start with the 4 hydrogen broad singlet at 7.0 parts per million. All right. So again, these have to speak, or this peak speaks to the hydrogens on the benzene ring, because the only types of hydrogens that give rise to a peak or peaks in the range of 6.5 to 8.5 parts per million are those that are attached to a benzene ring. Okay. Now, the 4H in this range indicates that there are 4 hydrogens on the benzene ring, which means that the benzene ring is di-substituted. And for di-substituted, we can have ortho, meta, or para. Now, again, the broad singlet sort of might lead us to a para where the 2 groups are the same. But let's look at the IR. And in the fingerprint region, we have a single peak at about 820 inverse centimeters. And what that does, if you check your notes, is that it does tell us that this compound is para di-substituted. So maybe we're going to run across a case where you have the 2 groups on the same in a para di-substituted position. Okay. But we do know that we have something here that's para di-substituted. Next thing I probably want to take a look at is the 1 hydrogen septet, because the only thing that could be is a CH. All right. Now, again, the benzene reading is 6 carbons. This is carbon 7. So that leaves us with a 3 hydrogen singlet and a 6 hydrogen doublet. Okay. So for the 3 hydrogen singlet, 2 possibilities, 3 equivalent CHs, which it can't be here because there's only 3 carbons left, or it could be a CH3. So that takes us down to 2 carbons and 6 hydrogens that are left, 1 peak for 6 hydrogens. So that means can't be 6 equivalent CHs, can't even be 3 equivalent CH2s. It has to be 2 equivalent CH3s. And these 2 CH3s have to be different than this CH3 right here. So let's see what we got. Now, if I think about these pieces that are here, there's really only one way to connect these pieces to give us something para di-substituted. One of them would have to be the CH attached to the benzene ring. The other one in the para position would have to be a CH3 attached to the benzene ring. You can't have 2 CH3s attached to the benzene ring because then you'd be done. So what has to be a CH, and it has to be a CH3, and this is going to be the CH3 that's different from the other 2. And then it fits very well that the last 2 CH3s would be attached to the CH, because if they're attached to the same carbon, that would make them equivalent. So 3 hydrogens, pick 1. Here's the carbon it's attached to. This is the only neighboring carbon. No hydrogens. 0 plus 1 is 1, singlet. This hydrogen, here's the carbon it's attached to. It has 1, 2, 3 neighboring carbons. 0, 3, and 3 is 6. 6 plus 1 is 7. It's an actual septet. For the 6, pick 1. Here's the carbon it's attached to. This is the only neighboring carbon. 1 plus 1 is 2, doublet. Now, let's talk about the hydrogens on the ring. So all 4 hydrogens are not equivalent. The one on the top carbon and the one on the bottom right carbon are equivalent. The one on the upper left and the bottom are equivalent to each other. So for A, we'd have two hydrogens. What about the splitting? Pick one. Here's the carbon it's attached to. Visit this neighbor, visit this neighbor. No hydrogens, one hydrogen. 1 + 1 is 2, double it. And then for B, we also have two hydrogens here and here. Pick one, I'll pick this one. Here's the carbon it's attached to. Here are the neighbors. No hydrogens, one hydrogen. 1 + 1 is 2, double it. So again, like we saw in the previous example, maybe the peaks are so close that it looks like it's just one continuous broad singlet. But in reality, what it should be is two hydrogen doublets in the 6.5 to 8.5 range.